Okay, so here's our next example. Let's move on to this other special right triangle. This one's called a 30, 60, 90. And again, that's referring to the angles of this right triangle. So we know it's a right triangle. So it has a 90-degree angle. The other two angles have to add up to 90 as well. Just because it is a triangle, everything adds up to, all of the angles add up to 180. So there's our right angle. If this angle is 30, then this angle has to be 60, because 30 plus 60 is 90, 90 plus 90 is 180. So that's why it's called a 30, 60, 90, and that's why the previous example was a 45, 45, 90 triangle. Now what we're going to cover here only works on these special right triangles, in particular the 30, 60, 90. Let's start out by filling out this conjecture and then moving on to some examples. Here we have this 30, 60, 90 triangle. In a 30, 60, 90 triangle, if the shorter leg has length A, okay, the shorter length is A. Shorter length, let's make a note, the shorter length is opposite of the 30-degree angle. So here I filled it out already, opposite of the 30-degree angle. So opposite is right across. That's what it means by opposite, right across. So that has length A. Then the longer leg, which is opposite of the 60, let's go ahead and write that down. The longer leg is opposite of the 60-degree angle. Has length of A times radical 3. A times radical 3. Now, it doesn't make sense now, but after we go through a few examples, then you'll see that it actually works. It's nice. And the hypotenuse has length, the hypotenuse, which is here, has length of 2 times A. So 2A is the hypotenuse, or you can say that this is 2 times the length of the short leg. Length of short leg. Length of the short leg. This one we said it was A times radical 3, or you can actually write it as the length of the short leg times radical 3. So there's the pattern that they're trying to get us to understand, that they're trying to establish, that you always go back to the short leg. It's either the short leg times radical 3 to get the length of the long leg, or you go the length of the short leg times 2 to get the length of the hypotenuse. And again, the hypotenuse is always opposite of that right angle. That doesn't change. Yeah? So let's take a look at how this conjecture came about. Understand it a little bit. Maybe this will help clear things up. Okay? So what we have here is we have the one on the left. The one on the left is an isosceles. It is an equilateral triangle, equiangular, where all angles are congruent. So they're all 60 degrees. So this one here is also 60 degrees, right? Each of those are 60 degrees. Now let's go ahead and let's cut this in half. So right through C, we're going to cut this triangle so that it makes 2 smaller triangles. And we're going to take one of these, right? We're going to take one of these triangles and copy it off to the right. We're going to be working with both of these 2 triangles, the entire triangle, and then also half of the triangle, just to see if we can make sense of this. We're going to say that the length of each of these sides of this equilateral triangle is 2A. So from A to C has length 2A, from C to B has length 2A, and also from A to B, that length is 2A, which makes sense because it's an equilateral triangle. Now, from C to B, right, C to B, just we said it was 2A, so from C to B, we're going to say that this is 2A. So that's where this comes in there. And this is, here's our right angle, so that means that this is the hypotenuse, right? Across from that right angle is the hypotenuse. Now, AB used to be It used to have a length of 2a, but we cut it in half, right? So that means that this point here is d. If we cut this segment or the side in half, that means each of these lengths is a. So from d to b is now a. A is opposite of this 30-degree angle, so that means that this is actually the short leg. That's actually the short leg. Now the only thing left to do is to find the length of CD. Let's call this B. And let's use the Pythagorean theorem to see if we can solve for B, if we can then tie it back to that conjecture. So let's go ahead and try that. Using the Pythagorean theorem, we have a squared plus b squared is equal to c squared. Let's do a little bit of substitution. A is the short leg, but what we have for the short leg is a, so we'll keep it as a squared, plus b, we labeled it the same, let's call that b squared, and then what we have for c is 2a, so it's going to be that quantity 2a squared. I know it doesn't make much sense now because we're not using numbers, but you'll see it all works out in the end. Now let's clean this up just a little bit. We have a squared plus b squared is equal to, now 2a, that quantity squared, we can take each of those individually and square them. So we have 4, 2 squared is 4, a squared is a squared. Okay. Now let's continue. Now we have is, let's go ahead and solve for b squared. B squared is, and solving for b squared, you get b squared is equal to 4a squared minus a squared. Let's clean that up a little. We can combine like terms on the right hand side, so we end up with, let's see, 4a squared minus a squared. We end up with 3a squared. The very last thing that we need to do is take the square root of both sides. So let's go ahead and do that. So we have b is equal to, let's see, we have the square root of a squared times the square root of 3. Well, the square root of a squared is just a, which is equal to a times the square root of 3, or a radical 3, meaning that b is equal to a radical 3. Oh, check that out, right? So everything refers back to the short leg. If the short leg is a, the hypotenuse is 2 times the short leg. If we have the short leg and we want to find the longer leg, what we have to do is take the short leg, which is a, and multiply that times radical 3, right? Short leg times, let's see, we have the short leg times radical 3. So it works, right? What we want to do now is let's put some numbers in here, because it's hard. Sometimes it's hard to see these in action if there are no numbers. So let's go ahead and put some numbers here and see how it works. And let's see how this works. And here we